Swayam Prabha. Digital India. Educated India.
Start a new topic, namely graphs. So graphs capture what is connected to what. And many things we deal with in computer science are graphs. These include things like social networks, friendship networks, collaboration networks, or computation networks. Namely, for instance, you have a digital circuit, it's connecting various gates with other gates. Or in a supercomputer, you could have nodes connected to each other using some connections. And that's also a graph, the way in which they are connected. More abstractly, you could have communication networks, transportation networks, or even knowledge is, things like citation of one paper to another, or the URLs, how various web pages point to each other. They all give you various graphs, and they come up all the time in computer science. In many of these applications involving graphs, you might often want to design graphs with good properties. For instance, if you're using your graph to decide which processes are connected to which others in a supercomputer, or which computers are connected to others in a network, or if you're designing a data structure like a tree, and that's something we'll talk about in more detail later. You would typically want graphs which have very few connections. These are what we'll call the edges between the nodes in the graph, because they incur hardware cost, or cost in terms of the algorithm having to look over many of these connections. So we'd like to have a few connections, but often we'd like to also have good connectivity. For instance, you would like to have many short paths between two nodes. So you don't need to necessarily go from one computer to another directly. As long as you can route it through other computers, you would be happy with that. So you'd like to have some connectivity property while still keeping this graph sparse in terms of the actual connections you put between, direct connections you put in between the different nodes in the network. Okay, so to understand what exactly this amounts to, we will be defining quantities like the degree of a graph and the diameter of a graph and so forth. So that's what we will be doing in the subsequent lectures. And graphs, to handle graphs, we need a lot of algorithms, and we do have a lot of very efficient algorithms for many problems, like searching in a tree or in a more general graph, finding the shortest path. So this is the kind of thing you will need to do when you navigate using, using a map app on your phone. It'll tell you the shortest path to take, and that's a graph algorithm. So we do have a very efficient graph algorithms for many of these problems. But on the other hand, there are also graph problems for which we do not have any efficient algorithm. And not just that, these problems are often rich enough that you could model other problems in terms of them. So this is a class of problems called NP-hard problems. We will not define it, but these are rich enough problems that can be used to model various other problems. But unfortunately, they also turn out to be very hard problems to solve. The traveling salesperson problem is one such problem. So we will be talking about all these once we have a formal model for graphs. We'll formalize this notion, and we'll stick to a somewhat restricted form of graphs called simple graphs. So what's a simple graph? It's simply a pair of sets, V and E, where the set V is just a finite set for us. And E is a set of pairs, unordered pairs, of elements from V. Okay, so think of V as a set of vertices or nodes in the graph, and E gives you connections. It connects the vertex A to vertex B, then you have the set AB as part of E. So E is the set of edges or the lines we draw between the nodes. We will stick to finite graphs, even though more generally you could talk about infinite graphs. And of course, the only interesting graphs are if the vertex set is not empty. However, the edge set could be empty. That is allowed in our definition of a graph. An important thing to note is that the graph only specifies this connectivity relation. It doesn't include the drawing of the graph, how you put down the nodes in a sheet of paper and draw a line or a curve between them to indicate an edge. That, where you draw the nodes and how you draw the edges, that is not part of the graph. You could draw it differently and it would still be the same graph. Okay, so since I said the graph captures only the relation, you should go back and think about using graphs for relations. So this is something we did already. And the difference between the graphs we talked about at that point to capture relations and the graphs we are dealing with now is that the graphs we use for relations were directed graphs. So they talked about pairs of edges, ordered pairs of this form, AB, to say that A is related to B. Whereas now we are only talking about the set AB, so or the unordered pair AB. So also earlier we allowed self loops in the sense that an element could be related to itself. In a simple graph, we do not allow these two things. So we do not. So if you were to write the relation corresponding to a simple graph, the relation being A is related to B, if there is an edge between A and B, that would be a symmetric relation. If there is an edge between A and B, there is an edge between B and A because the edge is just the unordered pair or the set AB. And similarly, it's irreflexive. There is all the edges require two distinct endpoints or two distinct nodes that they connect. So it would be an irreflexive relation. Okay, if you want to write directed, a relation as a simple graph, you could provide the relation satisfies these. So if it's a symmetric relation, you're supposed to have, whenever you have an edge AB, you're also supposed to have the edge BA. So given that, you could just replace the two directed edges by one undirected edge AB. So a simple graph can be represented as a symmetric irreflexive relation, and conversely, a symmetric irreflexive relation can be completely captured using a simple graph, with the understanding that an edge AB indicates two edges, the directed edges AB and BA. Okay, so essentially, a simple graph is something we have already seen. It's a relation of a specific kind. We could talk about non-simple graphs, and in computer science we often do, allowing say more than one. So first of all, they could be directed, and they could be there could be multiple edges between any pair of nodes. Instead of either having an edge or not having an edge. So for a simple graph, since the set E is a set, you cannot have two copies of an edge AB. You either have the set AB or you do not. But you could consider non-simple graphs, or these are called multi-graphs, where there's a multiplicity. So the edge set E is actually a multi-set. Or more generally, you could have weighted graphs where it doesn't have to be an integer. You can have an arbitrary weight, maybe even a negative weight for each edge. So we will, for now, not talk about these kind of graphs. We will stick to simple graphs. Here are a few useful examples. These are graphs with special names. The first example is a complete graph denoted by Kn. So there's a complete graph on n nodes. So there are n nodes and all possible edges exist. For instance, or rather the set E is defined as, so once you give me the set V, the set E is exactly this one set. It consists of all subsets of size 2. They're all edges. So to visualize, here is a graph with 5 nodes and all possible edges are there. How many edges are there? There are 5 choose 2 edges, or more generally, there are n choose 2 edges. So that's n times n minus 1 by 2. That's a complete graph. Another interesting graph is a cycle. A cycle is you could order the edges as v1 to vn, and such that the edges are of this form, from vi to vi plus 1. And so you have, say, v1, 2, 3, 4, 5. There are edges from 1 to 2, 2 to 3, 3 to 4, 4 to 5. And further, there is the edge 5 to 1. Okay. So those are the different kinds of, this is the last edge I mentioned. So these are the edges in a cycle. Of course, that is if you label the edges, label the nodes in that order. Another interesting graph is a bipartite graph. And what this means is that there are 2 parts, or there's a partition containing 2 parts of the vertex set. So the set V is partitioned into V1 and V2. So in this example, the left and the right vertices. And there are no edges within a part. So the edges go across parts. That's the condition on a bipartite graph. There should be a way to partition the vertices into 2 sets such that every edge goes across the 2 parts. There is no edge within a part. So edges are of this form, AB, where A comes from one part and B comes from the other part. We shall see shortly a cycle, if it is of even length, so not the example here. So this is odd, n equal to 5. But if it were n equal to 4 or n equal to 6, then you could keep the alternate edges in one part and the other, the remaining edges, alternate nodes in the cycle. So V1, V3, and so forth in one part, and the even V2, V4, and so forth in the other part, and you will end up with a bipartite graph. So we'll see this in a bit. And finally, complete graphs, complete bipartite graphs. These are just bipartite graphs where every possible edge between the 2 parts exists. So, every edge AB where A is in V1 and B is in V2. So bipartite graph has an edge set which is a subset of the edge set of the complete bipartite graph. And in this case, the number of edges is exactly equal to n1 times n2, where n1 and n2 are the number of vertices on the 2 parts. And we'll see more interesting classes of graphs as we go. An important basic concept about graphs is the notion of graph isomorphism. So if I give you 2 graphs, G1 and G2 with vertex sets V1 and V2, and some subsets of those vertices as their pairs of vertices as the edge sets, they could actually be just relabelings of the same graph. So, maybe in V1, I numbered the nodes as 1, 2, 3 up to 10. And here I numbered them, say, 0, 1, 2, 3 up to 9, for instance. And it could be the same graph, essentially, with just the relabeling of the vertex names, or vertex labels. So that's what graph isomorphism captures. If there is a relabeling so relabeling is essentially a bijection from one vertex set to another, such that once you do the relabeling, this edge set automatically transforms into this edge set. So E2 consists of exactly the same edge as UV under the relabeling. So if UV is an edge in E1, then FU, FV, the relabeled nodes, give you an edge in E2 and vice versa. So that's the only way you will get edges in E2. So here is an example. So suppose my G1 is this graph with nodes ABCD. So the set V1 is ABCD. And here is another graph G2 where the vertex set is 1, 2, 3, 4. And here is a bijection from V1 to V2 such that you can verify that the 4 edges that you see here under the relabeling transform into the 4 edges that you see here. So here there is an edge AB. Under the relabeling, it is 1, 2, and indeed there is an edge 1, 2. Similarly, AC becomes 1, 4, and there is an edge 1, 4 here. And BD is 2, 3, and CD is the last edge, that is 4, 3, right? So that they're all the 4 edges that you see on the right hand side. So this is a bijection from G1 to G2. Indeed, the labels, V1 and V2 could be the same set also. They don't have to be different sets. For clarity, I have shown them, I've given, this ABCD, this is 1, 2, 3, 4. You could also see, what this looks like in terms of, so remember a graph is a relation. So it's a symmetric, irreflexive relation. So we could use a matrix to look at a graph. This kind of a matrix is called an adjacency matrix. So the relation AB, is the adjacency relation. So we'll say A is adjacent to B if there is an edge between A and B. So that's like A and B are connected to each other. So in this relation, the adjacency relation, this matrix corresponds to labeling the rows as A, B, C, D, and the columns as A, B, C, D. The 4 edges show up. Well, there are 8 positions lighting up here. That's because each edge appears twice as AB and BA here. So AB would be this, and BA would be this, for instance. Right. So these are the 4 edges. And in our isomorphic graph, the isomorphism or the relabeling essentially corresponds to reordering these edges, these rows and columns. So here C and D got reordered. So that's saying you have to flip these 2 columns and then flip these 2 rows, for instance. So you would end up with this new matrix. Here, the labels are 1, 2, 3, 4 and 1, 2, 3, 4. And these 2 are actually isomorphic graphs. And if you just look at the matrices, they might look very different from each other. But as this isomorphism shows, they're actually the same graph, even though their matrices look different, even though the edge sets look different. And you could have multiple isomorphisms. So here is another mapping further from 1, 2, 3, 4 to W, X, Y, Z. And you would end up with another graph or another drawing. It's the same graph. Here I've drawn it to indicate that it's essentially the same picture as here, but tilted and relabeled. But it's probably more apparent here that it's a bipartite graph. And here flipping 2 and 3, reordering 2 and 3, if you reordered the rows and columns of this matrix, you would end up with this nice looking matrix, which shows that it's a bipartite graph. There are no edges within the first part. There are no edges within the second part, and it's a complete bipartite graph. So all the edges across the parts exist. In fact, this is K22, and this is C4. It's a cycle, and they happen to be isomorphic graphs. There is a graph isomorphism between K22 and C4. So in this case, these are small graphs. It was easy to see that all these different matrices correspond to the same graph. But in general, this becomes a computationally hard problem to check if two such graphs given as adjacency matrices like this are isomorphic to each other or not. So sometimes it's very easy to check, right? You can see that if they have to be isomorphic, then they should have the same vertex size, because there has to be an isomorphism, a bijection. And similarly, they should have the same edge set size, because there's a bijection between edges in E1 and edges in E2. So clearly, if the edge set sizes or the vertex set sizes are different, then they're not isomorphic. And you can develop many more properties like this. You can check many more properties like this. These are called invariants under isomorphism. And if two graphs have to be isomorphic, then it's necessary that they have the same value for these invariants or the same invariant properties. But we don't have an exhaustive list of easy to check properties such that if all those properties are satisfied, then we can guarantee that there is an isomorphism. So we don't have such an easy to verify strategy. In fact, there are no efficient algorithms known when the graph is large. There are pretty good non-trivial algorithms, and they do work very well in many graphs, even graphs which are not particularly small. But in general, so in the worst case, these algorithms could take a long time on large graphs. So we will not formalize these notions of efficiency right now, but there's just something to know that graph isomorphism doesn't have algorithms that are guaranteed to work on every instance quickly. In fact, a lot of people believe, no such algorithm exists. Some people believe such an algorithm is just waiting to be found. So we don't know, how efficient an algorithm eventually we might manage to find. But as of now, we don't have a fully satisfactory solution for the graph isomorphism, the computational problem of graph isomorphism. Okay, another useful notion about graphs is a notion of subgraphs. So a subgraph is another graph. A subgraph of a graph V is another graph with vertex set with a vertex set which is a subset of the original vertex set, and the edge set which is a subset of the original edge set. So that's all that a subgraph is, where the vertex set and the edge set are subsets of the original graph you are given. And of course, E prime should still be a valid edge set for the vertex set V prime. So E prime cannot have vertices that are not present in E prime. It cannot have edges between vertices which are not present in V prime. For instance, here is a graph G, and you could pick out some of the vertices. So V prime, so V has 5 nodes here, V prime has 4 nodes, and G has 4 edges here. That only 2 of those edges are retained in G prime. So this is a subgraph of this, right? you could imagine getting a subgraph using a process where you just first select V prime. So you cull out a bunch of vertices from here. So in this case, you decide to remove this vertex. But if you're going to remove this vertex, you have to remove all the edges that are incident on that vertex. So in this case, there's one edge you had to remove just because you remove this vertex. And further, you may decide to remove more edges. So in this case, there was another edge, and you just decided to remove that edge also. Okay, so to get a subgraph, you first remove some vertices along with all the edges incident on them, and then further you can remove some edges if you want to. Okay, so that is what a subgraph is. Of course, the original graph as it is as a whole is also a subgraph of itself when you decided to not remove anything, but you could remove. And the empty graph, in our case, say just with one vertex and no edges, would also be a subgraph of G. There is a notion of an induced subgraph where all you do is remove the edges, remove the vertices and edges incident on the removed vertices. So you don't get to further prune the edge set. So the edge set is completely determined by the original edge set and the new vertex set V prime. Okay, so that is what an induced subgraph is. So it's induced by the subset V prime. So you get to choose a subset of vertices, and then the edge set is induced by this set of vertices you picked. Often, if you follow these edges, where would it lead you, or how would it lead you from one node to another? Okay, so that's what we are going to formalize today using these notions of walks and paths. And to motivate this, we'll use one problem that we already talked about, namely the bridges of Königsberg. So remember the puzzle here, you have this landscape with a river flowing through 4 land masses here. So 2 islands and the 2 banks, and these land masses are connected via bridges. And the puzzle was to cross each bridge exactly once. So you have to cross all the 7 bridges, but you should not walk through the same bridge twice. And the question was, is it possible to find such a walk? Okay, so you could try going around, like this, being careful not to repeat any bridge twice, but then at some point you get stuck. And it turns out that it's actually impossible to solve this puzzle. And, but how do we know for sure? And we could do that, we could answer that by modeling this problem as a graph. So here is what a graph would look like. The nodes are simply the land masses, and the edges are the bridges. Okay, so this, as of now, it's not a simple graph because there are these parallel edges, these multi-edges, but you could simply add extra nodes, one for each edge. So you split up what used to be a single edge into 2 edges now, connecting a special node that you created for the bridge. Okay, so now there's a simple graph, and what we shall see is how to use this graph to formalize the question, the puzzle, and show that you don't have a solution for that puzzle. And this is indeed what Euler did way back, leading to the genesis of graph theory. So let's formalize this notion, these notions which would let us answer the puzzle. And the concepts we need are walks, paths, and cycles. So walk is just a sequence of vertices. See, these are all elements in the vertex set, V0, V1 up to Vk. So this is a walk of length K. And the starting node is V0, and the node where we end up is this Vk. So if it's a node, if you are looking for a walk from A to B, you would require that V0 is A and Vk is B, and any two adjacent nodes in this walk, so Vi and Vi plus 1, show up as an edge in the edge set. Okay, so this is exactly capturing the notion of taking a stroll around, going from one landmass or vertex to another through an edge. So if you had to go from Vi to Vi plus 1, so from the one island to the other island, you need to have a bridge between them. Okay, and the length of the walk is just the number of edges in a walk. So it could be 0 if you just start at a node and stay there, then it would be called a walk of length 0. And a special case of a walk is if the walk has no node repeating. In this case, it's called a path. Okay, so path is nothing but a walk, so it's a sequence like this, but there are no repeating, so you cannot have A and A in two places in the sequence. And another special case of a walk is what's called a cycle. It's almost like a path. You cannot have repeating nodes except the first and the last node are the same. So V0 equal to Vk. And we require at least 3 edges to be there. So if I write ABA, that is just going from A to B and coming back from B to A. We don't call that a cycle. If it is ABCA, then that would be a cycle. So a cycle has to be of length at least 3. That will be our convention. And so we require a cycle to be of length at least 3. It could be longer. And a graph is said to be acyclic if it has no cycles. So this is part of the reason we don't want to consider an edge to be a cycle, because every interesting graph has an edge in it. We don't want to think of that as a cyclic graph. That so just an edge doesn't give you a cycle, but if you have a cycle of length 3 or more, then we call the graph cyclic, and otherwise it's called acyclic. Another way to define an acyclic graph is that it has no, there is no subgraph of G which is isomorphic to the cycle graph CK for k greater than or equal to 3. Right, so that's the definition of an acyclic graph. And these concepts of walks, paths, and cycles, they will show up all the time. And this is essentially one of the things that sets apart, makes graph theory special. The kind of properties that we look at, the kind of structures we look at within the relation. So even though the graph is just a relation, these structures are what make graph theory graph theory. Another such notion that's important in graph theory is the notion of connectivity. So it's defined in terms of walks or paths. So let me define it in terms of paths. So I'll say that if there is a path between U and V, then U and V are connected. So they are not connected in the sense of there is an edge between them, but there is a sequence of edges you can take from U to get to V. So there's a path you can take from U to get to V. So U is said to be connected to V if there is such a path. And even though I defined it in terms of a path, you could define it in terms of a walk as well. And there's a little exercise for you to, so clearly if there is a path, there is a walk, because a path is a walk. The converse is not hard to see, and leave it as an exercise for you to prove that if you have a walk, you can, and if there are repeating nodes in it, you can snip out the pieces between repeating nodes, and you'll still get a valid path from the same between the same start and end points. Okay, so that's a definition of connectivity. And so you can define, you can capture that as a relation between over the vertices, right? So two vertices U and V are related to each other by this relation called connected if they are connected to each other. And it's an equivalence relation. You should confirm that it's reflexive, symmetric, and transitive. Reflexivity comes from the fact that there is a walk of length 0 or path of length 0 from a node to itself. And it's symmetric and transitive. So you should verify these things. So this is an equivalence relation, and if you can go from U to V, right, you can take a straw from U to V. Yeah, and the verification of the transitivity property is that if you can go from A to B and then B to C, then in terms of the definition of a walk, it's very easy to see that if you took the walk from A to B and spliced it together with a walk from B to C, so just concatenated it, you will get walk from A to C. Okay, so that's the transitivity property. And symmetry property is, I can just reverse the order of the list, and that'll give you a walk in the reverse direction. Okay, so it's an equivalence relation, and you could talk about the equivalence classes of an equivalence relation. So the equivalence classes of the connected relation are called the connected components of G. So graph is partitioned into connected components such that within each connected component, any pair of nodes can go from, you can go from any pair of node to another using a walk or a path. And across connected components, you cannot go. You cannot reach one connected component from another connected component because there are no edges crossing across them. Okay, not just edges, there are no paths going out of a connected component into any other connected component. Okay, so that's those kind of islands or pieces that are separated from everything else in the graph. That each such piece is a connected component. Okay, another notion that we will use to answer our puzzle is a notion of a degree of a node. And so degree is simply the number of edges incident on a vertex. So the degree of a vertex is just the number of edges incident on the vertex. So, in this case, for instance, you have this is degree 0, this is degree 1, this is degree, these two are degree 2, this is degree 3. Okay, so it's just a size of the subset of edge set which includes this vertex. So of course we are defining this assuming it's a simple graph. It's a weighted or a multi-graph, then the degree definition will have to be appropriately adapted so that you would count the weights of the edges. And here's a simple nice property that you would find useful often, which is that if I took the degree of every vertex and summed it all together, okay, so summation of degree V over all V in the vertex set, the number you will get is exactly 2 times the size of the edge set. So 2 times the number of edges. And why is that? Because when you go around summing up the degree, so it will be like 3 plus 2 plus 2 plus 1 plus 0. Every edge gets counted twice. Once when I was adding, the degrees here, and once when I was adding the degrees here. So this edge contributes 2 to this summation. So the total summation is 2 times the number of edges. I could take a graph like this and I could look at its degree sequence. So the degree sequence is an invariant under isomorphism. So it's some structural property that doesn't depend on how you label the vertices. So it's sorted by the degrees themselves, right? Not sorted according to the labels on the vertices. So so this 0, 1, 2, 2, 3 is the degree sequence for this graph. And yeah, as I mentioned, it's an invariant under isomorphism. So the first thing you could check when you want to check two graphs are isomorphic is check their degree sequences. If they're different, you're done. If they're the same, then there is no guarantee that they will be isomorphic, and you have to work further. Finally, we return to the Königsberg puzzle. So to capture this question of whether you can go around through every bridge exactly once, we define a notion of an Eulerian trail. So an Eulerian trail is simply a walk which visits every edge exactly once. So remember, a walk is a sequence of the form v0, v1, v2, and so forth. And I would say that you are visiting an edge if it shows up as vi plus 1 in the graph. Okay, and an Eulerian trail is a walk which has every edge appearing as vi plus 1 in this sequence. And here is the solution to the puzzle from this observation, that if there is an Eulerian trail in the graph, I claim that there can be at most two nodes in the graph that can have odd degree. And we'll see shortly why. And this would answer the puzzle, because the graph there actually had 4 nodes which all had odd degree. And we added some nodes corresponding to the bridges. They were all even degree nodes, but the original land masses, they all had odd degree. So there were 4 of them. And the claim here is that if an Eulerian trail is to exist, then you can have at most 2 such nodes. And why is that? So suppose there is an Eulerian trail, v1, v0, v1 up to vk. K is the number of edges. And take any node v, and I could look at the edges which are used to enter this node v in this walk. So these are edges of the form vi minus 1 vi, where vi is v. And also I can talk about the edges you are using to exit this node in the walk. So there are edges of the form vi plus 1, again where vi equals v. And since it's an Eulerian trail, all the edges incident on v should be taken. So you'll have to use each such edge to either enter v or exit v. And further, you cannot use the same edge twice. Right? So the size of these sets together is exactly the size of the number of edges, is the degree of v. And further, these sizes should be equal if v is not a start or end node, because whenever vi equals v, you have one node that is in the enter set and one node in the exit set. Right? So if you enter the node, you must exit the node. Under the node is a start node or the end node. So every node other than the start and the end nodes of the walk, these two sets have the same size, and they add up to the total degree. So the total degree should be even. Okay, so the 2 nodes we excluded are the end and begin nodes. They could be 2 different nodes, in which case there will be exactly 2 which have odd degree nodes, or they could be the same node, in which case there will be no degree to no odd degree node. In this case, it's called an Eulerian circuit. It's a closed walk. A circuit is a closed walk. So v0 equals to vk, where k is the length of the walk. And an Eulerian circuit is a circuit which visits every edge exactly once. And what we just now said is that if it's an Eulerian circuit, then there are no odd degree nodes. Okay, if it's an Eulerian trail, which is not a circuit, then there are exactly 2 odd degree nodes, the start and the end nodes. And if it's an Eulerian circuit, if there is an Eulerian circuit, then there are no odd degree nodes. In fact, it goes a little further. it's a sufficient and necessary condition. So if there is no odd degree nodes, then you must have an Eulerian circuit, provided it's all in one connected component. So no odd degree nodes and a single connected component, or at least all the edges appear in a single connected component, then you can argue that an Eulerian circuit must exist. So I leave it as an exercise for you to write a complete proof for this, but I'll give you the basic idea here. So the first observation is that if there are no odd degree nodes, then it must be cyclic. Right, if there are no odd degree nodes and there is at least one edge, so if it's not an empty graph, then it must be cyclic. And why is this? You should think of picking up an arbitrary node in this connected component and starting to walk around until you encounter until either you should walk around without repeating edges. And the claim is that you will not get stuck until you have repeated a node. Okay, and the first point you repeat a node, the part of the walk from the time you encountered that node for the first time and the second time gives you a cycle. Why is it that you will not get stuck? That's because there are no odd degree nodes. So it won't be the case that you entered a node and you cannot exit it without repeating an edge. Okay, so first thing is to argue that it must be cyclic, and so having no odd degree nodes implies that it must be cyclic, provided I'm excluding the pathological case of all nodes having degree 0, in which case there is a trivial Eulerian circuit, right? So once you know that it's cyclic, you can think of removing a cycle. So there is at least one cycle which is a subgraph of this graph. Suppose you remove this cycle, you delete every edge that falls in this cycle. And what you're left with will still be a graph which has no odd degree node, because every vertex either had two edges deleted from its deleted, which are adjacent to it, because this vertex was in the cycle, or none. So in either case, the degree goes down by 2 or by 0, so it remains even degree. Okay, so you still have no odd degree nodes, but of course, what could happen is that even though you originally had only one connected component, when you deleted the cycle, you might break the graph into multiple disconnected and multiple connected components. So you can, but they're all smaller, so you can inductively obtain Eulerian circuits in each connected component, the remaining graph. And then the last step is to stitch all these together into a big Eulerian circuit, So you start by taking the cycle you have, and one of the Eulerian circuits that you obtain inductively, they must intersect somewhere. That's how the graph got disconnected. And then you argue that you can stitch them together. You can rearrange you can kind of concatenate, splice together the two circuits into one big circuit. So this is something you should argue. And then you can keep doing this with every other Eulerian circuit you generated, always adding them on to the big circuit you're building. And at the end, you would have one big circuit. It has to be Eulerian because you never repeated any edges, and you covered every edge, right? Every edge is covered in between these Eulerian circuits you generated inductively and the cycle you removed. So this would give you the final Eulerian circuit. So this is something you should argue yourself, and note that this actually gives you a recursive algorithm as well, kind of a simple algorithm where the two steps are finding a cycle by just walking around until you repeat a node and stitching together two Eulerian circuits if they intersect at a node. A problem that sounds quite a bit similar to Eulerian circuits is the question of finding a Hamiltonian cycle. So remember, Eulerian circuit we just saw, there is a simple characterization of when an Eulerian circuit exists in a graph, namely all edges are in the same connected component and there are no odd degree nodes. And also there is a simple algorithm that can efficiently find an Eulerian circuit when it exists. Hamiltonian cycle is, as I said, a problem that sounds quite similar. The question is now to find a cycle that contains all the nodes. So being a cycle, it means you cannot repeat nodes. So it's a sequence of nodes that are connected by edges, and you should cover all the nodes in the graph, and you should cover them exactly once. So unlike an Eulerian circuit where you're trying to cover all the edges and you're free to pass through the nodes multiple times, here you are trying to cover all the nodes and you should go through each node only once. And in the process, you may not cover many edges. That is okay. Okay, so the problem is, given a graph, does it have a Hamiltonian cycle? And if it has one, can you find it? Unfortunately, even though it sounds a lot like Eulerian circuit, it's a very different problem, and we do not have any efficient algorithm to check if a graph has a Hamiltonian cycle. In fact, it's what's called an NP-hard problem. So as we mentioned earlier, it's a problem which has a lot of structure, rich enough to model a large class of problems, all these problems called NP problems. And it's widely believed that these kind of problems do not have any efficient algorithms. So it's not just that we have not found one, it's quite likely that there isn't such an algorithm. So graph problems, so Eulerian circuit is something which is easy. Hamiltonian cycle might sound a lot similar, but it's very hard. And then there are also these problems like graph isomorphism, which I mentioned as a problem which is believed to be hard, but it doesn't have the same kind of structure or richness to it that, at least so far we don't know if it's an NP-hard problem. It's believed to be not to be an NP-hard problem. It's still believed to be a hard problem in terms of we don't think it has an efficient algorithm, but it's not rich enough to model all these problems in this class called NP. Okay, so graph problems give you a rich variety of algorithmic questions, and they are used to study complexity of computational tasks abstractly in what's called computational complexity theory. Of course, there are many other kinds of problems, but graphs give you a nice framework to see many of these problems together. Okay, one last thing in this lecture is a notion of distance. So this is again something related to connectivity in graphs. Given a walk, given two nodes U and V, which are connected to each other, so there are walks between them. There is at least one walk between them. Among all the walks, consider the one which is the shortest. Maybe there are multiple shortest walks. And I claim that each of these shortest walks between this pair of nodes has to be a path. Okay, and this is a fairly easy thing for you to prove. You can prove it by contradiction. Suppose there's a walk, and if that walk is not a path, then you can trim down that walk and still get a walk between the same endpoints, and that would give you a strictly shorter walk. So if you start with the shortest walk, you couldn't have trimmed it down. So you'll be able to trim it down if it is not a path, if there is a repeated node. So it has to be a path. Okay, and therefore, whenever we see there is a walk between two nodes, we might as well say there is a path between these nodes. So we already saw It's an if and only if condition, and connectivity could be defined using either. Now, this shortest walk or shortest path is of great interest in many applications of, when you're modeling problems as graphs. For instance, when you do navigation, what you're often interested in is finding the shortest path between two nodes in the graph, where the edges here are, roads, segments of the road, or if you're doing communication, routing, you would be the segments, the edges would be segments of optic fibers, for instance. In many problems, it would be convenient to also attach a notion of length to an edge, so that you don't have to make it into short segments of the same length. But in our, for us, in notion of simple graphs, we will not attach any notion of length to an edge. If you want a longer edge, you just concatenate a bunch of edges together into what you would like to model as a long edge. Okay. Now the shortest distance would be the quantity of interest when you are when in the map navigation problem, the routing problem, communication, but also in some other problems where you're modeling a graph, using a graph to model a probabilistic process. And it would be the shortest path that corresponds to the most likely outcome of this process. And this would be of interest in many AI applications. Okay. So this length of the shortest path is called the distance between the two nodes. Okay, so between nodes U and V, there might be multiple shortest paths of the same shortest length. That length is called the distance. Of course, if there is no path between U and V, then this is not well defined, in which case you could take it as infinity. So there is no well-defined distance between nodes which are not connected to each other. Formally the distance is this. So you go over the set. So W, capital W is a walk. So you go over all walks. So I write UV walk to mean it's a walk from U to V. So go over all such walks, all such sequences, and for each sequence find its length, and the distance is a minimum quantity among the set of values. Also define something called a diameter. Diameter is the largest distance in a graph. So this kind of tells you how well connected the graph is in some sense. So there's the furthest you will need to go from. So there's in a connected graph, you can go from every node to every other node, and the furthest you will need to go is called the diameter. Of course, if it's not a connected graph, it can be infinity. So formally, the diameter is, so you go over every pair UV and look at the distance and find the pair that maximizes the distance, and that distance is the diameter. Again, there could be multiple pairs UV which all have this maximum distance. So just plugging in the definition of distance here, it's the maximum overall UV between U and V, the length of the walk. Okay, so that's just expanding out the definition of distance. Okay, let me wrap up with this, quick slide on applications of shortest path. So I already alluded to them. So the obvious examples were, navigating in a map or routing in a network. Notion where you might want to give lengths to the edges. I mentioned this you can use it to model probabilistic systems. So just to wrap up, one example would be you could model speech production using a graph, the probabilistic process of speech production. So the nodes would correspond here to various states, vocal cords and lips, various positions. The lip is open or closed. You as you make your sounds, your mouth would go through different states. So it transitions from one state to another. You could model this as going from a node corresponding to one state to another node. And the length or the weight on this edge would correspond to the probability or the ease with which you would do this transition. And in this case, the shortest path would correspond to, if you model it properly, the shortest path could correspond to the most likely sound that would come out. Okay, so this would go into a model for speech recognition, for instance, and finding the shortest path would be a subroutine you would need while solving the speech recognition problem.